So our second talk is going to be from Vinayaka. So Vinayaka is a compiler architect at Intel. He joined recently. Before that, he worked as a staff software engineer at Polyhedral Labs under Professor Uday. So he did his bachelor's in computer science from Sri Jayachama Rajendra College of Engineering, and he did his master's in Master of Science from IASC under Professor Uday. Without further ado, I'd like to ask Vinayaka, please take it away.
Thank you. This is working, right? Yeah. Thank you. Let's get started. So the talk or the presentation actually is on polyhedral analysis using MLIR Affine Dialect. So this is a continuation of a previous talk, but since there are many new people and last time's feedback was also that there were not many examples, and so we will do a recap of whatever we had discussed last time, and we will go till we discuss something called affine fusion. It's a transform. Yeah, we'll start. So yeah, structure and the agenda, it's a discussion on the publicly available concepts. It's not just my work. It's not a talk on my work. So it's a publicly available upstream repo from which this discussion is, on which this discussion is based. And what we are going to do in the affine dialect or MLIR dialect or in this talk is to we are going to reduce the breadth of the concepts that we want to introduce. Only smaller set of concepts will be introduced, not the full-fledged affine dialect and MLIR, so that we can kind of go depth first and reach till affine fusion. So you will see that the examples that you will see are very simple ones, but the dialect or the tool that we are going to introduce is a lot more powerful than whatever is going to be discussed. So this is kind of an introduction so that you can go back and check affine fusion or MLIR on your own. So this is a starting point. This is just an introduction. So in the agenda, we'll discuss, we'll recap whatever we had discussed on in the last talk. We had discussed MLIR, what is MLIR, what is affine dialect, what is an iteration domain, what is dependence. And we had just given kind of a teaser on what is fusion. We're going to discuss that and in a little more depth today. That's the end of the talk. Yeah, at any point of time, if you have any questions, stop. We can discuss that. So, okay. I think this slide is self-explanatory. This is usually the compilation strategy that we have. I think everybody understands. Different front ends are there, different back ends are there. Simple strategy is to lower everything into LLVM IR, do all the transforms in that, and maybe this edge, if you have a different backend, you will have your own edge to that. Instead of going from M into N compilers, you kind of give M plus N compilers. This is a strategy. This is a known strategy. Let's say, what is the problem with this strategy? And so I'm going to kind of build up why MLIR was needed. What was the motivation for that? So this is a pseudocode. This is not a programming language. I have just written it. So this is an SSA value. This is a function. It takes a tensor of, let's say, 4 cross 8, float 32. Some operation is there. I don't know what it is. Takes the input, creates the value T1, transposes, creates the value T2, and returns T2. Simple enough program, right? Let's say if the programmer had written something like transpose and then followed up by another transpose, and it's a 2D matrix, then you can immediately say that this is useless, right? Transpose of a transpose is the same thing. It is useless. Many of the times, such transposes can be hidden inside other bigger operations. For example, let's say, in this example, what I want to show was, instead of just, let's say, lowering it all the way to LLVM IR, I want to represent these things at an abstraction level of loops. Again, this is a pseudocode. This is how the transpose will look like. This is a transpose nest. It is going to load from ji and store it at ij. This is a transpose nest. And this is the last transpose that we had seen in the previous slide. It is this. And that sum operation, it had a lot of code on top of it, and it resulted in, at the end, It transposed and gave out the result. This is a very common thing. It can happen all the time, right? Now, if I want to optimize this and I want to get rid of this transpose of a transpose. So now what I have to do is understand that this is a transpose, then understand that this is a transpose, make sure that there is nothing in between, and then instead of giving out mem, I will give input mem. This is what I will have to do. This is a tedious task at this level of abstraction, because you knew at some point that this was a transpose, you broke it down, lowered it into a lower abstraction level of loops, and now you understand that this is a transpose and then delete it. So you are coming down and going up. So this is happening because you are losing, or in this, from a higher level abstraction, you directly went to a very low level abstraction, very fast. You should have taken a pit stop in between. That would have been better. So many languages implemented this. This is some front-end X. They implemented something called XIR. It is again a higher level abstraction, lower than front-end X. Then they made it into LLVM and then backend, and then they did some transforms in this, at this stage. Again, the same problem happened where every front-end started writing its own middle-end IR. So LLVM IR is there, front-end is here. In between, many dialects started getting populated. Many abstractions started getting populated. This was a problem. So MLIR said, we will follow this principle of progressive lowering. We'll slowly lower things and not go all the way in one shot. And that abstractions that whatever we call, so far we have been calling, in MLIR world, they are going to be called dialects. So similar things or similar operations that are at the same level of abstraction are going to be clubbed into what is called a dialect. Dialect is basically a pit stop. You go from one pit stop to other, and if you are lucky, you reach a pit stop very early, and someone else has already developed the road till the end. For example, stable HLO is a popular dialect. Everyone is talking about it now. Stable HLO is at a very high level, a pit stop. PyTorch, let's say if you have a PyTorch program, if you lower it to stable HLO, people mostly have built whatever has to be built to compile it and run it till the end. So you just have to create one H at the top. If you come up with your, let's say, hardware, a different hardware, again, it is lowered till a very low level, and at that level you can take an edge out and you can create one more dialect for your hardware and bridge that gap. Rest of the things, TF2 all the way till your dialect will work. This is the principle of progressive lowering. So MLIR is a sub-project under LLVM. This is a good link. I think, yeah, if you search for it, it will come up. So getting started is, I highly recommend that you should look into it. So it's a novel approach to building reusable, extensible compiler infrastructure. So whatever I have been saying is only one part of it. It does a lot more things. I'm just describing whatever is needed for this talk. Progressive lowering is needed for this talk. Dialect is a collection of types and operations that work on the same level of abstraction. We have seen this. MLIR is not just an infrastructure to create all this. As soon as they created this infrastructure, they found that, okay, these are abstractions that are mostly needed by everyone. So some dialects, they became part of MLIR. And Affine is one of them. So we are going to see what is Affine. Affine is a publicly available dialect. Many other dialects are available. Affine is one among them. Again, it's because it's popular, it's easy to reason. Many programs, they can become Affine and they can transform at that stage. It's a popular dialect. It's an open source dialect, and yeah, we will dig deeper into that. So instead of just introducing what is Affine dialect, what are the operations in it, what is the type, I'm just kind of going into the deep end here. So this was an earlier pseudocode, right? For this is a transpose nest. Look only at the top part of it. This was the transpose nest on some pseudocode. So it is very similar. This is actually Affine snippet. This is very similar to that. This is an Affine for, it goes, let's say I, it goes from 0 to 4. 4 is an exclusive. It cannot become 4. It is 0, 1, 2, 3. It cannot become 4. J goes from 0 to 8, which means it maximum it can become 7. And then you are loading from Ji, you are storing at ij. All the SSA values usually have this percentage prefixed with them. Usually there are types. This is a memory reference of 4 cross 8 cross float 32. Affine has many more things. It can take steps. There are many different ops like affine parallel and different ops. Affine vector load is there. We are not going to touch those things. We have 3 ops now: affine for, affine load, affine store. Now I'm going to say why it is affine. This is just some for loop and some load and store. Why is it affine? We're going to go to that. But these are the things that we're going to discuss. So at this point, if you believe that this and this are equivalent, that's fine. We can go ahead. If there are any questions, I can stop me. Okay? Okay, I had highlighted some things here. Probably I forgot to say. So there are. Is there a laser pointer? Okay. So why is it affine? What is the definition of affine? The mathematical definition of affine is linear plus constant. You have a linear combination of things and then you add a constant to it. That expression is called affine. 2i is affine. I square is not affine. Is that okay? So in this dialect, the restrictions are present on, let's say, this 0 and 4. Those are the bounds of the affine for, right? It has to go from 0 to 4. The second loop has to go from 0 to 8. Those are the 2 bounds. Call them lower bound and upper bound. And let's say these are axes. J and I are axes. All of these have to be affine in terms of some values. I'll define again what are the values. They have to be affine. If I had placed this J, or I had made this J, instead of J, I had put J star J, then it doesn't become affine. It will immediately throw an error. The parser will say, I cannot parse it, it cannot be affine. Similarly, if you say affine for 0 to 4 instead of 4, or 0 to 8, if you had done sine of I, sine as in sin function sine, again that is not affine. That would fail. So affine, by the restriction on the IR is that the bounds and the axes, in our case, in this discussion, all have to be affine. When I say affine, they have to be linear combinations plus a constant. Maybe there is a constant, otherwise constant is 0. Actual affine dialect, upstream, yeah. I affine, yeah, it's affine. That's good. Yeah. I had that question, but you asked it. Good question. So the question is, will all the programs go through this? What if something doesn't go through this? Can anybody give an example of a program that will not fit into an operator? Loop with I square. A gather operation, a scatter operation, where instead of loading from a location like I, you go to another array where you go index into that and get that value, and from this location you're going to load. That's a kind of in an indirection. That's not affine. So in such cases, those will not become affine. The beauty of MLIR is it will allow you to represent 2 different levels of abstractions to coexist. So you can have an affine loop, and let's say that gather operation came and you could not convert it into affine. Leave it as scatter. Whatever my dialect dot scatter. I'll just keep it. I'll take care of it later. I'll convert it into, let's say, LLVM directly. So it will allow you to kind of mix these different dialects together. That happens all the time. Yeah. 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 Okay. Got it. Yeah. Yes. Mhm. Mhm. No. Good question. Good build up again. So what he is saying is, instead of writing it as an affine for, I'm loading it, I'm going to initialize some location to 0, load, and every time I complete this, I'm going to just do +1 and store that, which is like plus plus j or j plus plus whatever exactly he's saying. It is not affine, as in, if you load from 0 and then store that thing, and then basically you're loading from some location, and that is your index now, right? You loaded a value and that is your index. That's like a scatter, that's like a gather operation, where instead of loading from I, I'm going to load from B of I. It's not affine. So if what usually happens is, if someone has to write it, they will make sure they write it in this way. If they want the affine analysis to work, while lowering itself, somebody will convert and write it this way. Okay? Yeah. They are same. Yes. So usually when people say linear, I can say linear in x and y. Usually it becomes ax by, but there is always a c. Ax by plus c equal to something. That c, because of that c, it becomes affine. Otherwise, it's just linear. Okay. Okay, affine. We restricted the whole kind of loops that we want to get and the accesses that we are going to work on. We have restricted them to make sure all the bounds and accesses are going to be affine. Otherwise, you will not even parse it. It will never come to you. Okay, that's taken care of. The thing that is restricting here, as in, I'm going to narrow the discussion. Yeah, sure.
So you said MLIR allows different dialects to coexist. What if one part of what has been reduced to affine uses a certain context that's coming from a different part of your code which cannot be lowered to the affine dialect?
Yeah.
So in that case, how is it?
Good question. So let's say there is an affine loop outside, and inside that there is another loop. In MLIR world, there is something called SEF is a dialect, which is lower than affine. It doesn't have all these things. You can write SEF for starting from this, ending at this, whatever you want. So let's say there is an affine for, and inside that there is an SEF for, which doesn't have all these restrictions. All the analysis that you can do have to stop at that level. Whatever remains inside, let's say there is an SCF for, and you load from some location inside that is an SCF load or memref load. You cannot say it exactly comes from this location. You will not be able to reason. So you can assume the worst case, that this can be anywhere from 0 to, in this case, 4 or 0 to 8. So analysis will have to stop. But in most of the cases upstream, if they see that there is a non-affine loop or non-affine construct inside, they give up. They just say, I cannot process it, so I'm not going to process it. Yeah, the restrictions I was going to place are, I'm just going to say that this is a linear combination. You can multiply constants with it and then add them up. But affine dialect actually upstream, it can support seal div, floor div, mod with respect to a constant. You can do I mod 2 here. It will still work. Analysis will still be accurate, but for this discussion we are going to restrict that. They even recently introduced I mod n, where n is a constant. I don't know its value at compile time, but I'm sure that it is constant. That is called semi-affine. That's again out of the scope for this talk. So we're going to just stick to multiply, add, multiply with constants, add them up. Valid values. What are the valid values? All the constants are valid values, and inside this affine for, the top affine for, inside that I becomes a valid value. Inside this loop j becomes a valid value. You can make sure, you can basically convert this affine for j equal to 0 to 8. You can start it from I. It's still a valid value. Okay, so do all programs go through Affine Direct? I thought I'll ask questions. This question is already asked. This is answered as well. Do all bounds need to be constants? They don't have to be. You can place, instead of 0, you can place %i here and it will still work. What operations cannot be represented affine? This is done. Mul add only 2 operations allowed in affine expressions. This is also something we have answered. But for this talk, this is yes. Upstream affine can actually handle floor, dev, mod and all. Okay, just to make sure that you are comfortable with affine nests, can somebody guess what this nest is doing? Matrix multiplication. This is a matrix multiplication. It is summing up at C, multiplying A and B. Very similar to a C code that you would write. AJK values. Okay. Can somebody guess what this is? Rel. It's a ReLU operation. It is, if it is positive, it is going to keep the same value. If it is negative, it is going to store 0 in its place. It's a ReLU operation. So, yeah, this is what we will see a lot in the upcoming talk. So, it's good that everyone is comfortable with this notation. So, recap is not done. I'll just introduce what is fusion, and then again we'll start with the iteration domain and such things. So, this is one example. I think this is doing a transpose, and this is a square nest. You do a transpose and then you square it and then you store it. 2 nests. So probably in the original program, somebody wrote a transpose and then wrote a square. If you run this exactly this way, you will have these 3 memory locations, load from one, store into one, and then load from that and store into this. So A to B, B to C. You would do this. First thing you will need to load from these and store. I think I am over explaining this. I think you would easily see that if it was fused like this, it would have been better. You would have eliminated B. Instead of going from A to B, B to C, you would have loaded from A and without storing, finished the computation and then stored it. This is what we want to achieve. This is affine. This is fusion. I should not say affine fusion. This is fusion of 2 nodes. It's a common transform. This is fused. Before we go into affine fusion, whenever we say fusion, it doesn't mean that affine fusion is the only fusion. There are different fusions. When you have a graph of different computations feeding into one another, you can fuse them at very different levels. Affine fusion is one among them. It's powerful enough. But you can probably fuse at a very higher level or even a lower level. Fusion is not that it has to happen at affine level. What we are going to introduce is also called slice-based fusion. It's a compute-intensive process, but it is very generic. It can handle a lot of nests, different kinds of nests. But somebody might also write something like this. So this goes from 4 to 8, 4 to 8, and those bounds match with this loop. It's just a permutation of this, and all the accesses are simple enough. So I'm going to analyze this and I'm just going to fuse it. That is also a naive fuser. People write it. It works well and very quickly for many things. Affine fusion that we are going to discuss is slice-based one. It is more complicated and mathematical. But such fusions also exist. We'll see where such fusions do not work later. So I'm going to go into the the title was Polyhedral Analysis using Affine MLIR. Right? So we know MLIR affine now. We have to go into what is polyhedral and polyhedral analysis. That's the part of recap. So before we go into that, any questions at this stage? So next step onwards is all polyhedral. Question is, are all the fusions slice-based? Yeah. It is separated out. Yeah, you can do other dialect fusion using these utilities. It's not tied to MLIR affine. it just exists in MLIR. You can do linear fusion as well. No questions? Okay, so we'll go into the polyhedral side of this. This is mathematical, a lot of linear algebra will be needed now. So the motivation or the reason for introducing all these is we are going to use these and fuse. All these are going to be used in fusion. Okay, so x equal to 1 represents a line, right? We'll go back to mathematics. X is there, y is perpendicular 1, x minus 1. This is the rearranging and this is the line. Simple. I'm just reusing the previously created slides. Again, we'll go to the same x equal to 1 or x minus 1 equal to 0. There is something called a column picture of looking at things. When we say column picture, it means we will, instead of looking at lines, we will think of vectors. People are smiling there, you know. Good that it reminded you. It is Gilbert Strang's lectures, if you have followed, he talks a lot about column pictures. So instead of thinking of these things as lines, I'm going to say it's a set of all xy vectors such that there is a 1, 0 vector here. The dot product of them is 1. The component of all those vectors along 1, 0 is 1. So which is again the same line, the set of same vectors. So instead of looking at these things as geometrical lines, we are going to start looking at these in terms of points, a set of points. Again, infinite set of points, but still a set of points. We are going to extend it. Instead of x equal to 1, it's now going to be x greater than or equal to 1. Again, in the column picture, it means the 1, 0 vector still is here. All the vectors such that their dot product with 1, 0 is greater than 1, not just equal to 1, equal to 1 and more. So all that half of the iteration space, all the set of points that lie on that side. I haven't pointed those things, but they exist there. Similar thing can be extended for less than as well. It's simple. Any greater than, if you multiply with minus 1, they change basically. So this is x less than or equal to 5, 5 and all the x's on this side, all the vectors on this side. Right? Two half spaces. So the reason half space is very simple. A line kind of is a demarcation. It cuts the space into two halves. Yeah. We're going to define something called an iteration domain now. People might have already guessed what this is going to be. Take an affine for, nested affine for like this, it's a nest. This can be represented in terms of these inequalities now, which basically means x goes from 1 to 6, right? I'm going to say x is greater than 1. It's one inequality that I get. X is less than or equal to 5. 6 is not included. So x is less than or equal to 5. Similarly, and I can write these things. Now this is an intersection, right? For example, x greater than or equal to 1, it was this line. Everything that was on the right side of it. Less than or equal to 5 was everything on this side of it. I'm basically intersecting as in this set intersection this set. So the top and the bottom are still not covered. Y covers it. Y has to be greater than 2, greater than or equal to 2, less than or equal to 4. So all that lies on this side and it should lie on this side. This is the iteration space of this loop nest. Right? So as long as all these bounds were affine, this could still be done. I've just taken the simple constant bounds here. But if somebody had written I, then you would have written x equal to y, or x greater than or equal to y, and then you would have gotten a cross line like this. We have an example like that. We'll see this. So this is the iteration space of this. That's clear, right? So yeah, we should start thinking in terms of a set of points. These are not lines or half spaces. These are sets, and constrained by a system of equalities or inequalities. I haven't introduced inequalities here. Still inequalities are there. Equalities can be there as well. In this example, there are no equalities. So, okay, this is somewhat involved now. This and this are equivalent. This is how it is going to be represented in MLIR. The structure is called FLVC, flat linear value constraints. Pretty simple to understand. So think of this as a multiplier 1 equal to x plus 0, 1 into x plus 0 into y plus 1 into minus 1. Assume that there is greater than or equal to 0 at the end, which is this. Similarly, the second one and the rest. So this and that are equal. So if there was an equality, it would be represented as a separate table here. And the assumption would be instead of greater than 0 at the end, it would be equal to 0 at the end. It's not here, but we will see that example. Good. So, okay, what have we achieved with this? No extra information is collected actually. Whatever was there in the affine nest, it's the same thing that is represented in a different format in terms of inequalities. So I want to introduce a little more complicated one to kind of drive home the point why we need it. This 1 to 6 is there, so this is visible. So it should be, every point should lie on this side of this line, and including this line, and on this side. So the constraints on x are clear, right? It should be between these two. That's clear? Now affine y, that's interesting. Let's go to the upper bound. It has to be less than or equal to 4. That is represented. So it has to be on this side. Now I say the lower bound, the other constraint has to be, it has to be greater than 10 minus x. X was defined just outside. Which basically means, where is it? This constraint, y should be greater than or equal to 10 minus x, which means x plus y minus 10 equal to 0. This is the line, right? X plus y equal to 10 is this line. Because this is greater than 0, the points have to lie on that side, right? Not this side. You can just take any point in this one. The point here would be 5, 6. 5 plus 6 is 11, which is greater than 10. And this constraint is saying that everything on this side should be taken and not this side. So essentially, how many points do we have in the polyhedron now? 0. It's an empty set. We don't have a single point. So let's say you construct an affine iteration space, and you have this check. Once you represent in these constraints, there is a library that is already present. Pressburger set library is what was being used. There are different libraries that are available, which will take these constraints, and you can ask these questions. So set-based questions. For example, is this set empty? Is a question you can ask. It will return true or false. You can take a set and subtract another set, and then ask the question, is it empty? All this union, difference, intersection you can do. In this case, we are going to ask the question, is the set empty? In this case, it is going to say empty, in which case I can remove this. It's a useless loop nest. Without this analysis, it is very difficult to decide whether we want to remove that nest or not. If you construct and ask that question, is empty, somebody will say true or false and they're trustworthy, you can remove it, right? Yeah. In MLIR, currently, Pressburger set was there. They were building something called FPL, Fast Pressburger Library. I'm not sure if it is included or not. It's in progress. All these integer set library things are somewhat slow. They are known to be slow. But there are a lot of improvements that have gone in last few months. This is okay?
So in this case, since there are no points in the particular polygon,
Yeah.
this can be denoted.
This is still affine. It just doesn't have any points in it. You can delete it. Yeah, it has zero effect. You can delete this. Okay, so yeah. You can do other things, but they all fall back to the same. So you can form these equations of, and you can instead of thinking in terms of sets, people ask this line and this line whether they intersect or not, are they parallel? There are tests to work it out, but they all fall back to the same thing. That LLVM, I'm not sure. But yeah, my knowledge of LLVM internals is very limited. I don't know. If we don't do these FLVC things and if affine dialect didn't exist, would somebody eliminate this nest or not? That is the question. Yeah, I don't know. Yeah. Lower and upper bounds of X loop were not integers. Ha, correct. Good question. So they are called symbols. They are just not covered in this talk. They are basically they are compile time constant. So what you are going to say is n, define n outside, and you don't modify n inside anywhere here. It is still affine. It is still reasonable. As in, you can still do finish analysis on this. What evaluation? I think, yeah, I was suggesting that. I think those will be the fallback things. We will have to fall back to them. But I have seen some internals of it, they all finally do the GCD test, or some tests will be there. And similar things are being done by Pressburger set, so I didn't yeah, explore that. But I think they all fall into the same bucket. Okay? Oh, anybody wants to take a guess, how should I change, let's say, excess bounds so that at least one iteration should be there? Yeah. So instead of this, I can move. So this line is saying that everything that has to be on this side is covered, right? And this is also there. So I want to target this triangle. So I can move this line here so that I can get at least one or two iterations. Correct. Okay. So we will define something called affine relation. We had defined it earlier. This is a recap again. Just like between two sets, you have A and B, and you can define relation from A to B. They are related in this way. You can have affine relations because this is essentially a set. So from one set to another set, I can define relation, and that relation can be affine. Now, what do I mean by that? I think it will become clearer with an example. A very commonly used affine relation is access relation. It's an access relation. We're going to define it. There are different kinds of relations. One of them is access relation. So you have iteration space, all those points. It doesn't mean that that point has to kind of only access ij. If the point is ij, it can access ji. It can access 2 star I, something like that. In this case, the ith iteration is accessing I plus 1th location. So it's not one-on-one. So there are two different spaces here, right? Iteration space is there. It goes from 1 to 5. And there is a memory access space. It accesses something. It's a different kind of, it's a different set. It is not an iteration. It's a memory space. So you can establish a relation between them as long as the accesses are affine. So I'm going to call this I plus 1 as M, mth location. M is equal to I plus 1, very simple. This column and this column already existed, right? This is I greater than 1, I less than 5. This was already there. I introduced another column inside it, that is M. M lower bound, upper bound are not defined for now, but I introduce an inequality and I say m equal to I plus 1, or minus I plus m minus 1 equal to 0, which is m equal to I plus 1. So this is an affine relation. Now again, we will ask the question, some questions like is empty, to actually use it. But is this clear? It's an affine relation. Now, let's see if we can answer this. What I want to check is, affine access, is it going out of bounds or not, is not really controlled by the IR. It is not going to throw an error. If you access minus 1th location, it is not going to say you should not access it. It will still allow it. So how do I check? Let's say I want to check if an access went out of bound, if an access went below 0. How do I check? I think we have enough information so far. We can probably try to answer it. So this access relation is there. Now what can I do to ask or answer that question? Okay.
You have the inequation for I, so you substitute like the relation between I and M there, and then you get two inequations in M. And then you can use that to see, like, because you have already defined the size of M, so you can know whether the axis is going out of bounds there or not.
Good. One way of doing it. So what he is saying is, in fact, that is the way that is everyone does. So this is a constraint system. I cannot just become anything. It has to be within this. And I constrains M because there is an equality. So find the lower bound of M, find the upper bound of M, see if it is out of bounds or not. Can you? That's one. Correct. That's how usually it is done. I was going to fall back to the is empty check, where I was going to say, I am going to add another constraint here, another row, M less than minus 1 into this. And I'm going to ask the question, is it empty or not? Which again is similar thing. If it is less than minus 1 and if there is a point, it will say, okay, this I which is related to M is not empty, that there is a point, which means there is someone who is accessing minus 1. Okay. Is empty only tells you whether it's empty or not. Which iteration is accessing it is something that's not going to be given by this, but it can answer this question. Good. So, okay, so we have introduced iteration domain, we have introduced affine relation. This is kind of the last polyhedral construct that we are going to introduce now. Again, it's a more complicated constraint system based on the similar rules that we have followed. Now there are two ops so far. We had considered one op, one nest. Let's say there are two operations. Let's say they are in two different nests. One is a store, another is a load. Affine store, affine load. And we will construct the access relation of store op. It will look like this, right? First, initially all the columns will be IVs of the store. IVs are induction variables, all those I's and J's. They will be there, and indices of access will be there, like M, M1, M2. In case it's a multi-dimensional memref, it will be M1, M2. And finally there is one, constant or not. Similar thing can be done for load op. Okay. We will see that example of this. Last time it was missing, so I have added an example. So we can do an access relation of load as well. And let's say we merge those two. This and we place this beside one another. We can do that, right? Basically, wherever we don't have any values, we'll fill it with zeros. So all the few rows of this will come and will fill zeros at that point, and bottom will write all the rows and fill zeros. We can construct this. So until this point it is okay. Otherwise we'll see an example. So two access relations, I just place them one beside another. Now I'm going to add one more extra set of constraints. All of those are equalities. I'm going to say, because they are accessing the same memref. Oh, I forgot to tell that. They are accessing the same memref. Otherwise there is no point in doing it. Which means the dimensionality of the memref is same. The M's will be the same number. The M1 will be here, so M1 dash will be here. M2 will be here, M2 dash will be here. The same dimensionalities will be there. And now I'm going to equate them. M1 equal to M1 dash. M2 equal to M2 dash. M3 equal to M2 dash. I can go on for each dimension. So what have I achieved at that stage after adding all these things? So initial set of constraints were there, they were on axes. Two axes were there. Now I have constrained them to be equal on each dimension. They are right. I have also said that these iterations of source or store, and these iterations, and they have to write to same location. Yeah. So this is called a dependence polyhedron. It is okay if it is a little bit confusing because I haven't shown an example at all. It is very difficult to follow. But this is a theory of how we construct a dependence polyhedron. This is another polyhedron. It's a relation between source IVs and destination IVs, constrained in such a way that if you say, I want destinations 1, second, 1, 2 iteration, who is writing to it in the source, you can get that answer using the dependence polyhedron. We'll show the example, but yes, it's a data dependence. Somebody is in RAW, WAR, those dependencies. Okay, so far at this point, any questions before dependence polyhedron? Any questions on dependence polyhedron? Okay, we will see the examples and we'll again come back to see if there is any questions. I want to switch to a terminal so that I can show how the dependence polyhedron looks. And let's see. This is 64 cross F32 is being a 16 cross 4 cross 32. It's a reshape of, instead of one single dimension, it is making it a two-dimensional nest. So this affine nest and this affine nest, they are clear, right? We'll see all the polyhedrons that we have constructed so far. Iteration domain, affine relation of each of these, and finally we'll construct a dependence polyhedron. Okay. Let me see if I can switch quickly. Let's say, okay, producer, how should its iteration domain look like? It's a single dimensional nest, so there should be two rows, one greater than 0, one less than 63 should be. This is correct? Okay. Consumer iteration domain, 16 and 64, there should be 4 constraints. This is fine. Producer access relation, it's an identity. So M is I here. Right? So yeah, this is the same, right? These two were anyway there. These are the constraints on the I, and I equal to M. This is the equality that is there. Consumer access relation is a little more interesting because load A here, it is 4I plus. Am I running out of time? This is 4I1 plus I2. This is a consumer access relation. Again, all these things are inequalities, and this is 4I1 plus 1I2 is equal to N. We'll construct this and we'll see. 1 second. I wish I could show both of these here. So what I did here was, I1, I2, So the first access relation had I1. So I have even named the nests like that. So this is I1. It should go from 0 to 63, I2 should go from 0 to 15, and I3 should go from 0 to 4. Those things are still there, right? I1 should go between these two, I2 these two, and I3 are these two. Those things are there. So access relation had one M there. Right? It was all -1. If you see there, it was -1 something, right? So this was the M column. And let me see if I can highlight it. This was the M column. It was -1. So I just placed two things together, and this was, I basically made M1 which of this and M2 of this equal, which means it will look like 1 -1 of that on that row. I can eliminate them. And that's why the actual dependence polyhedron doesn't have any M here. So if you wanted to introduce, you would introduce an M here, and you could still write all the equalities, but you could eliminate them because M1, M dash, they would be equal. And finally, you would be left with a relation between I1, I2, and I3. You could eliminate M, they're equal. This is the dependence problem, but this is the best example I could come up with. This is easy to follow. It basically is saying how I1 and I2, I3 are related. They are constrained so that they have to access the same location. Okay? Which basically means they can be between all these things, but if you give me I2 and I3, let's say, I will calculate what I1 is. That's the thing that I was saying. With this equality, if someone says 0, 1 iteration of this is loading some value, who is going to write to that value? 0, 1 of this. 0, 1 of this is 1, and who is going to write to that value is I0 has to be 1. So you can construct who wrote to this in the source. That's the dependence polyhedron's purpose in this case. Different purposes are there. We are going to use this. I think, yeah, we have 5-10 minutes of discussion left. So for fusion, what we are going to do, this is a slice-based fusion. Kind of, this is the main part. So let's say I am at just above this M, this line, and at that point I ask this question. At this stage, I know which is I1 and I2. I1 is I1, I2 is I2. This stage. Now who is writing to this location? I can get that value in terms of an expression, and I can copy this whole nest, or whoever is writing, whichever iteration is writing to that location, I can bring that and place it here. Right? I'll show it in action. I think it will be clearer. Concentrate on this. So this already existed. This is a second loop nest, 16 cross 4 nest. These two already existed. Now I introduce something else here. Now this is the slice of the source. Now I brought the whole source, entire source here. Instead of running it from 0 to 63 all the way, I said at this stage, this is going to load from arg1, arg2, right? For this arg1, arg2, who is going to write? And I asked that question, it said this, it's difficult also. this is an affine map, right? So you can think of it as arg1 star 4 plus arg2. That iteration is going to write to this. So just write it here and then use the same value. This is the slice brought in. This is a one iteration loop. It goes from this and this plus 1. It's a one iteration loop. It is exactly one iteration which was going to write to this. So I brought that one slice here. That's why it's called a slice. This is easy to follow, hard to follow. Correct. So using the dependence polyhedron, we generate those maps. Yeah. Yes.
Form or equation, whatever you call it, and then generate that map.
Yes. It is going to say for this location who is going to write it.
Exactly.
A lower bound, give me a lower bound and upper bound.
Upper bound, exactly.
In this case, it's an equality, so it's exactly one iteration is going to write to it. So we basically write this one trip count loop here.
Correct, yes.
But yeah, there is a code which detects this lower bound and upper
Exactly,
bound.
right, yeah.
And that's called a slice calculation. I didn't include it here. It would be a longer talk. But yeah, using the dependence polyhedron, somebody detects it. Yes, so it is basically saying arg1, R2, how should they be combined so that you get R3 here?
So the affine map is essentially like, so that line essentially is showing the conversion between different spaces, right? Between the two different
Yes.
affine spaces.
Yes.
And the first affine space is the one which is the one essentially in the second loop, and then the second affine space is the one
Yes.
inside. Okay.
Yes. This was a destination iteration space, that was a source, and there is a mapping between them. You copied the whole source and then you adjusted the loop bounds so that they only basically run whatever is required.
Is there a geometrical way to visualize this, like you visualize for the lines wherein you were drawing intersecting lines for in a 2D plane? So here we have three variables. So could we have tried to visualize this in a 3D space?
Correct. It's just difficult to draw, that's why I didn't include it. But as long as it's 3D, let's say in this case, when I started making the slides, I thought I would do it. That's why I introduced a one-dimensional nest and a two-dimensional nest, so that it can become a three-dimensional picture. I just couldn't finish it. But yeah, there's a way.
Relation, that part should always run. On the top of that, you also need to run the slice-based fusion pass.
Yeah.
And only then you'll be able to do this.
Yes.
Right? And none of this can run if you do not know if the iteration boundaries are constants. Like this cannot run if it's a dynamic shape.
It can run. I just
Can
didn't
run dynamic
introduce it.
shape as well?
Yeah, you can basically have another column which is n, which is a constant. Compile, it is guaranteed that it is constant, but you don't know its value.
Oh, okay.
It will still run. Basically, dynamic shapes is what you are.
Exactly, but are you saying, no, but it's a dynamic shape, then how do you say it's a compile time constant?
For example, a tensor or an input that you send.
Yeah,
Once you send it, you have sent it. You
Correct.
won't change it.
correct.
So I'll say first dimension of this unknown memref. I'm going to call it m. That is going to remain constant throughout the program.
Yeah, I got you. So basically what you're saying, even in the case of dynamic shapes, the dependence polyhedron would still remain the same.
Yeah.
At least the equation, at least the map would remain the same.
Map would remain the
Probably
same.
D0 and D1 iteration might change, but at least the map would remain the same.
Yeah. There'll be extra columns added. They are called symbols.
Exactly.
Whatever I have introduced are only dimension. There are things called they are symbols.
Okay, that makes sense.
When you have floor reviews and mods, there are more things that are added called local variables. I didn't include all of them.
Rather than a finite set of points.
You have an unknown set of points. It's
yeah.
still bound. You don't know its size. But if somebody asks the question, how many iterations will it run? You will not be able to answer it. But let's say you have a dynamic shaped add and then dynamic shaped square. you still have the same dynamic shape. You will be able to fuse them. The analysis will still work for fusion, just that it will not answer the question how many exact iterations it will run.
Okay. So other question is that, so do we need the for loop here, because it seems to be running just one iteration.
Just one iteration. That's a good question. So this is before this, you can see this. Before the loop promotion, this is the comment that I have added. It basically looks like this at the end. It will be eliminated. It's just one iteration loop. It will be eliminated. I just wanted to show how the slice sits there, and then it gets promoted.
So that will be part of the transformation, or
Yes,
just
it's part of the transformation. Loop promotion is a part of fusion. Yeah.
So when you said compile time constant, effectively any value that you are using must remain the same across the duration of your affine transform,
Analysis.
whatever you're doing. Okay.
Yes.
So let's say you have two separate affine operations in the same program,
Yeah.
and maybe you're receiving a tensor and you're performing two separate affine transforms on it,
Yeah.
and you're modifying the tensor between these two transforms in a non-affine manner.
Okay.
So for each individual affine transform, that value does not change across the transform, but it is not constant throughout the program itself. So in this scenario, can polyhedral analysis be performed on it?
It will take the conservative approach. It will say that something is happening which is not affine, and that's why I'll not. Let's say I won't fuse this into this
Right.
because I don't know what is happening in between.
Got it.
It cannot reason about. So it will take this fallback approach. If it doesn't exactly know what can it do, it will not do it.
But within those separate regions of affine transforms, it can perform completely.
Its own, yeah.
Right.
Let's say A, B, and then there was a C, and you had to fuse B and C, and there was nothing in between. It will still fuse it.
Got it.
It will not bring something from top and fuse it. Needed. There are two loops. Ignore this affine apply for. Don't ignore it. I'll just remove it. Iteration loop that is removed now. Load, mul, and store, they were there in the source. They are still here. And whatever two operations that were there, they were reshaping, they are still here. So at this stage, we still don't call it the fusion has completed. Fusion internally calls something called affine scalrep. That's what I wanted to show. So if you see here, %1 was calculated and it was being stored. Exact same value was being loaded into %2, and then that was being stored. First thing what we will do is we'll do a store to load forwarding. If you are storing and then loading, instead of storing, you can just use %1 in its place. So this will become %1, and it will remove the load. Right? You have calculated a value. If you want to store it, but you just use the same value, don't load it. So this line will go away, and then it will recognize that there is no one using alloc 0. Whatever value had to be sent to alloc is being sent on its own. So effectively it will look, after all this, it will look like this. It will remove those, yeah.
But that is basically dead code elimination.
Dead, in this case, dead store elimination, yeah.
So is that a part of the affine transform, or is that handled by a separate part of, or a different pass?
It is affine because it will still say, okay, this is being written. Is there someone using it? Let's say just because you are writing to a memref A and someone is loading from it, it will not say someone is loading.
Right.
It will say this is writing to 0th location. This is loading from 1th location. Even then it can eliminate.
Okay.
This is affine analysis, but it is not inside affine fusion.
Okay.
Sometimes we just call it inside affine fusion.
But this is still done using the affine dialect itself.
Affine dialect, affine analysis, all of these are fine.
So the complexity of this analysis would be exponential only, right?
It's high. I don't know. Yeah, it's high. That's what I know. Because all these
Yeah,
is
the
it
ILP would
empty, all these things internally, they're expensive operations. questions? Any other questions? I think I am done here. But anyway, out of in case someone is interested, uh, there are depths of fusion. It's not just fuse all the way innermost all the time. You can fuse it just above one loop, or you can step inside two loops and then fuse there. I'm talking about the materialization of the slice. We did it innermost just now. There's something called depth of fusion. There is also cost of fusion. It's not like fusion is always good and it's amazing, everyone should do it. There are costs associated. That's probably some other talk. I think most important one everyone is interested is the fusion driver. So far we saw how loop 1 and loop 2 got fused. But who decides which loops to fuse? Probably if you fuse A to B and then to C, it is better, or A to B and then stop, then it is better. So someone outside decides whether fusion should happen or not. That's the driver. Fusion analysis is pretty stable, it's good, it's working fine. Fusion driver is something that needs a lot of improvement. Upstream as well, according to me. Yeah, that's, yeah.
So as far as this fusion is concerned, or some other transformations based on loop, what are all other analyses like these fusion analyses are used at MLIR level?
You can say, is it contiguous? So let's say there are some iterations, and are they accessing or loading from contiguous location? So is access contiguous is an important check. This is about vectorization. About dead store elimination, again, is empty is there. Different set differences are taken a lot of times. So we want to say something is being done, similar thing is being done later. Probably this is a superset of whatever is being done. So I want to see whether this is a superset or not. So I want to take a difference and see if it's empty or not, in which case difference is used. Any other questions?